So this question is a review of what we talked about on Friday. And in retrospect, I might have gone through this unit not in the best order. Maybe I should have switched Friday and Monday, what we talked about, but bottom line, we'll get all the information across. So we did a one sample z-test for proportions. You got a p-value of 0.045. Significance level is 0.05. In reality, the null hypothesis is true. So did we accept or reject the null hypothesis on the basis of our p-value?
We rejected it.
We rejected it, but the null hypothesis was true. So that means there was an error that was made. And our, was it type 1 or type 2? I'll just say we rejected the null when we should not have.
Type 2.
That is a type 1 error. Rejecting the null when the null is actually true is a type 1 error. So I know it's kind of a silly way of presenting it on Friday, but it is something that I think is helpful, and I hope you find it helpful to think back on the story of the boy who cried wolf, that in the first case, the townspeople rejected the null, that there wasn't a wolf, when the null was really true. They rejected the null was true, type 1 error, that was the first thing that happened. Then they failed to reject the null when the alternative was actually true. So that's a type 2 error. That's the second thing that happened. So if that is helpful for you, it's hard. It's one of the harder things, I think, to keep the type 1 and type 2 correct. So the answer is A. All right, that is good on that. We'll move forward now. Here we go. So we are going to be looking at primarily the one sample t-test from you. This is chapter 23, the second part of it. And hopefully if you already read it, this is going to be pretty straightforward. So we are, let's just start with this. So teenagers are supposed to get 8 hours of sleep, but I don't think that's true for you guys. So we're going to record the number of hours you sleep. Oops, didn't mean to show that yet. We'll do that later. So what I want you to do is just put a stamp right here, just round to the closest average amount of hours of sleep you get, and put a stamp above those, or just a little dot. So we've got, what we're going to do now is we are going to calculate X bar and sample standard deviation. So I'm going to hopefully count this up correctly. I think there's 2 data points right there overlapping. I'm going to call that as 2. Maybe I'm wrong, but anyways, so there's 1 right here, 4 in this, 1 here, 1, 2, 3, 4, 5, 6, 7, I think right there. 1, 2, 3, and 3. If I add that up, that's 13, 14, 18, 19 data points. And that's about right for this class. So maybe I'm double counting 1, but we'll just go with that data. Okay, so here's what we want to do is I'm just going to create a list. And I'm not going to do anything fancy with it. I'm just going to take that and I'm going to put 1, 3 in. I'm going to put 4 5s in a row. So 5, 5, 5, 5. And then 1, 6, 7 7s, 3, 4, 5, 6, 7, 3 8s, 1, 2, 3, and 3 9s. 1, 2, 3. All right, so now that I've got 19 data points put in, I am going to run a 1 variable stat calculation for list 1. And I want you guys to have these numbers available. Hopefully you know how to do it. You're not just waiting for me to do the calculation. But when I do this, I see we have an X bar of 6.789 with a standard deviation. I'm using sample standard deviation, which is S sub X, the way they write it here, of 1.619. That's a 1. Something happened there. It was weird. So there we go. Those are the numbers we're going to be working with in a second when we get into our calculations. Because now what we want to do is we want to test this. We're doing hypothesis testing. We want to figure out, is this evidence that teenagers really don't get the appropriate amount of sleep, or is it still possible that you do? We'll come back to these numbers for the as we keep moving forward, but let me just move us ahead. Okay, so we're going to test this, and the first question is: are we working with proportions or means as we move forward?
Means.
Means. So remember, proportions are going to be, p hat, and they're going to be between 0 and 1. And we can phrase questions like this as proportions. I could say the true proportion of teenagers who get more than 7 hours of sleep is blah, blah, blah. And we could turn it into a proportion. We can. But we're working with means. We're trying to figure out the average hours of sleep for a teenager. And generally, with a lot of means problems, you're going to have some kind of a value outside of this range. But you can have a problem where you're working with means that falls between 0 and 1. For instance, maybe we're trying to figure out, we're going to test the hypothesis that the average length of a fish in a pond is 0.3 0.3 yards. So yes, 0.3 is between 0 and 1, but it still means here. So make sure you're reading the context and you're trying to figure out, is this means from a data set or is it the proportion coming from counts? And this would be kind of the difference between categorical data right here and quantitative data right here, going back to unit 1. All right, so it's means, and we want to write the appropriate hypotheses right here. We've got null hypothesis. Any idea of what our null hypothesis would be right here?
Is it mu equals 8 or
You
whatever?
got it. We are working under the assumption that you guys do actually get 8 hours per sleep. And just to conceptually, well, let's finish the hypotheses first. What would the alternative hypothesis be?
The mean is less than 8.
There it is. So as we go through this, I want to make sure it's conceptually very clear, because I picked up that there is some confusion on this. We are assuming that 8 hours of sleep is what you guys are actually getting, that teenagers in general are actually getting this. You are my random sample, okay? And from this, can we infer that there's no way teenagers are getting 8 hours of sleep? Or is it still possible? And so we're going to construct a sampling distribution that has our null hypothesis right in the middle. Now you guys are going to be on the left side of that. We know that. Now, are you guys so far to the left that it could not have happened by random chance? And this is the only probability, just that small tail over there? Or are you somewhat close to the mean? And so there's a, it could have just been random chance. Maybe if I got a different sample of teenagers, then, it would have been closer to 8. So what we're trying to figure out is this, wherever this ends up right here, this is my test statistic, meaning the actual kind of z-score, if you want to consider it that, though we'll get into that more later. So the actual, quote, z-score is the test statistic, and the area inside there, that is the p-value. And so if the p-value is too big, that means random chance is probably to explain, and we can't reject the null. If the p-value is really small, then it probably was not random chance. It must have been something else going on. You guys really don't get 8 hours of sleep. We're going to investigate that. Okay, so before we move on and start doing some calculations, what conditions do we need to meet?
Normal.
It has to be normal. So I'll put that one down there. We'll come back to the normal test in a second. What are the other tests we have to meet, conditions that must be met?
Random.
It has to be random. And
Independent.
10%.
yeah, independent / 10%. So in this case, it would be 10%. But if we had independent trials like with free throw shooting, then that would also qualify. So there we go. And so let's just run through it. Random. Would you call this a random sample?
I don't know that we
Yeah.
could because it's just one class.
I think in the strictest standards of research, this wouldn't qualify. We're going to make it count, okay? But I think I'm going to put, I'll just put kind of a dash there. No, this was not the best example of it, but we're going to move forward. Just understand that caveat, and it's okay. This is all for fun and for educational purposes. All right, 10% condition. Did we meet that?
Yeah, it's
Yes.
definitely less than 10% of all teenagers.
That is definitely true. We met that. And just for another reminder, I've said this 100 times, but the 10% condition allows us to use a simpler calculations, the ones that we know. All right. Technically, if we violated that 10% condition, we would have to use some corrections to get a more accurate answer. We're not worrying about that because we meet the 10% condition. And for normal, what does anyone remember what we have to do to check for the normal, for an approximately normal distribution when we're dealing with means? And to be fair, we only studied this once before with confidence intervals. Does anyone remember what our sample size needs to be?
It just has to be greater than 10. Is that it?
Okay, so you're thinking of the large counts condition. When we are working with proportions, we can do n times p and make sure that's greater than or equal to 10. Of course, n times 1 minus p. We can't do that when it's means because we don't have a proportion to work with. So we have a different standard for means. Okay, there you go. Jose said it in the comments. N has to be greater than or equal to 30. So if we have a big enough sample size, we're good enough. Or does anyone remember the other thing that we can use? I'm going to give you guys a little bit of a hint. Population is
If it's like greater than 500 or something.
no. So the other one, just to remind you guys, and it's important that you guys kind of internalize this concept because it's not on the formula sheet. You do need to know this concept. The population is approximately normal. So if the population is approximately normal, we're golden. If the sample size is greater than 30, that's good because let's remember what's happening. This is really using the simple. And so what's essentially happening is when we have a sample size of 30 or greater, we are comparing our sample to a sampling distribution with a mean that is our, presumed population mean. And when your sample size is 30 or greater, this sampling distribution will be approximately normal. If it's less than 30, it could still be skewed. All right. So if the sampling distribution is approximately normal, then we're good to go in that sampling size or sample size of 30 or greater. So just to say it again. So I think, is it fair to assume, because our sample size is not greater than 30, is it fair to assume that the population would be approximately normal?
No.
Okay. So we might violate this one. We'd have to add a caveat. We're not doing so well with our conditions for this one, but we do know one thing. We do know that we have bounds on this. You can get as little as 0 hours of sleep or as much as 24 hours of sleep. All right. And I would guess for teenagers, it should be somewhat normally distributed. I doubt anyone's getting 16 hours of sleep at night. I think it might average, now I don't think this is mu necessarily, but I do think it's fair to say the population is normally distributed. And let's say it hovers around 7, with 5 and 9 being 1 standard deviation away. Is this true? I don't know. For our purposes, we can say that it is approximately normal or it's not, and just add a caveat at the end. So we can just say, no, we failed this one. And at the end, we'll just say, keep in mind, we might not have met the normal conditions. So take these results with a grain of salt. Phrase it however you like. So we might or might not have met our conditions. We're going to move forward. And we want to remember, this is going to require you going back to your formula sheet. And what we want to do is, sorry, lost my train of thought for a second. I want you guys to tell me what the mean and standard deviation formula is for a sampling distribution for means. So I want the mean for sampling distribution of means, and I want the standard deviation for sampling distribution of means. Okay, so we can see the formulas there, and if you didn't find them or kind of just got completely lost in this question I was asking of you, hopefully now you can go and look at the formula sheet and you can pin down where these formulas are. So sampling distributions, very important concept with all that we're doing with hypothesis testing. All right, let's see what's going on. Now, moving forward with our hypothesis test, do we know the population mean?
Yes. No.
Well, I mean, I think that's kind of fair to say yes with a question mark. So we don't really know the population mean, but we are going to assume a population mean. And what is the assumed population mean?
8 hours.
8. So right here, we're going to say that this is 8. Now, we're testing to see if that's true or not, but we're going to assume that. Now, we obviously don't know the population standard deviation. We've got no information to indicate what that might be. So here, we're going to have to switch this to our sample standard deviation. And now we can use the values we came up with before. I have forgotten them, but luckily it's on my calculator. Our sample standard deviation was 1.619. Our sample size is 19. So we can calculate this real quick. So I'll just put it to 3. You could keep going, 0.3714 and so on. But there we go. That's what I got. Hopefully you guys got the same. So when it says right here, what will our sampling distribution mean and standard deviation be? Well, here's the mean, here's the standard deviation. We had to calculate the standard deviation, but the mean we're just using, we could call it mu sub naught, because it's our null hypothesis. Okay. So we good with that? I'll assume so. So now we want to draw a picture and calculate this test statistic. All right. So let's start off with this. I'm going to give it a long tail on the left, just in case what happens in this class is the same thing that happened earlier. So we have our distribution here, which is 8 as the presumed mean. And then, of course, our standard deviation of this is going to be 0.371. So that would make this 7.629. And then so on from here. I'm not going to calculate the rest, though. It's a good idea to show that. This would be 8.371 and so on to the right. We know we're not going any further to the right. So approximately down, well, we can go ahead and calculate it. 7.629 minus 0.371 is 7.258. Then minus 0.371 again gives us 6.887, and then 6.516. All right, so I wanted to show those numbers because I want to go back to our one variable stat. We calculated our sample mean at 6.789. So we're going to be living about right here. Here's our X bar. So we're trying to figure out the probability of getting this value or more extreme, that area right there. And going back just to restate conceptually what's happening, we're going to convert this into essentially a z-score right here. So this z-score, when we convert it, is our test statistic. So that's going to involve some transforming of the data. And then we're going to calculate this area right here, which is our p-value. Okay, so let's actually do the calculations at this point. So for the test statistic, we are going to be doing X bar minus mu divided by our standard error, which is the sample standard deviation divided by the square root of n. And maybe I should write out, I'm doing this a little bit in reverse. I should have done this first. This is straight from the formula sheet where it's stat minus parameter divided by the standard error. So there's your test statistic. So now I substituted for means, what we're going to work with. And then I can now substitute in even further. Mu here is 8, and we calculated our standard error at 0.371. So now I can finally do the calculation, figure out what our test statistic is. All right, and I got negative 3.260. Now your test statistic might be a little bit off from mine, but what I did is I didn't actually use 0.371. I went and recalculated to get more precision and divided by the exact number, which is always a good idea. You should be in this ballpark though. If you were a little bit off, you should be in the ballpark. Okay. So now what we did before with proportions is we called this our Z. The test statistic was what we called Z. But remember, just like we did with our confidence intervals, this is a different kind of distribution. It's a t distribution, not a normal distribution. I know we were checking for normality earlier, but we're technically using a t distribution. So this test statistic is called t, which explains why we call this a t-test, not a z-test. Luckily, the name kind of gives it all away. Okay, so we got a t test statistic of -3.260. And just using your statistical intuition, do you think this is going to be significant or not?
Yes.
Okay. I hope you guys are thinking this is going to be significant. From the diagram we drew right here, and this is why that diagram is so important. From this diagram that we drew, and from this test statistic right here, we should be able to infer that it's highly unlikely that we get this. And look at where the p-value is pointing in that diagram. That area under the curve is very, very small. I don't know the number, but it's very small. And with that, that's going to tell me that this is highly unlikely just to happen by chance. That I picked 19 random people who happen to sleep way less than 8 hours per night. Okay. So again, we'll kind of go over this conceptually more as we move through it. But now we need to jump to the next part of this, which might be a little bit confusing. Because we are working with a t distribution, our test statistic is a t-value, and we have to consider the degrees of freedom. It's not as straightforward as just a normal CDF calculation, because what we would have done if it was a test for the z-test for proportions, I just said, oh, here's my test statistic right here, and I'll just do normal CDF with, this is my bounds, right? But it's not that straightforward. It's not much more complicated, but it's not as straightforward. So we have two methods for checking the p-value when using a t-value. So p-value and t-value. So I don't really like calling it a t-value, but when we're using t as our test statistic, we can use the t-table, table B. Okay, and let's kind of walk through how to do this. We had 19 people submit a response. So degrees of freedom is one less than that. So we're using this row right here. And we got a test statistic of -3.260. So what I want to do if I'm using this, and we're going to learn another way which you'll probably prefer, but this is a good thing to understand how to use this table. I got -3.26. I'm going to ignore the negative. All I care about is the absolute value of this number. I'm going to go over from the left to right until I find where this number would fit in. So 0.688 starts on the left, and I keep going over. By the time I get to here, it's 2.101. Okay, so I keep going. 3.260 fits in right here. All right, I don't know where exactly it falls between those two, but I do know it's going to be between these two p-values. So what you're seeing here, the tail probability, shows us our actual p-value. Okay, so I can't get more specific than this. What I do know is that my p-value is going to be less than, well, here's the higher number, 0.0025, 0.0025. That's going to be the upper limit of my p-value. And the lower limit is right here, 0.001. So we'll calculate this exactly in a minute. But just for now, keep in mind that it's going to be between those two values. Okay, and while we can't get more specific than this, we already know that we never said what significance level we were going to use on this. Should have done that to begin with. But it doesn't really matter at the end, because whether we're using a 0.05 or a 0.01, what would our conclusion be? Is this statistically significant or not?
I'd say no.
Okay, so remember,
Yeah, it is. Yeah, it
okay,
is.
there you go. Remember, for it to be statistically significant, our p-value has to be less than our significance level. No matter what, it doesn't matter what the exact value is, the highest value it could possibly be is 0.0025. And we know that that value is lower than either of these significance values right here, significance levels. So we can conclude right now that we will reject the null. You guys don't get 8 hours of sleep. All right. So that is the process. Are there questions right here? I kind of want to stop, make sure that that process is making sense.
Yeah, it makes a little sense. I might just have to practice it a little bit more to
Okay.
remember the
I will,
process.
okay. I will tell you that this is probably not going to be the method that you use, but I think this does a really good job of helping you conceptually understand. Notice that we're seeing the number of standard errors away that we have to be for this to be considered statistically significant, depending on our degrees of freedom. So since when we land in that range right there, that tells us we at 18 degrees of freedom, we had to be 3.2 standard errors away up to 3.6. And we're going to be within this range of a p-value. And remember, your p-value, just to show you one more time, is going to be this area under the curve. That's what we're actually seeing. That's why they call it the tail probability. All right, this was a one-tailed test. We're only interested in values that are less than the mean. So we didn't need to double our p-value. Okay, so that is one method you can use. That method is a part of statistics because some people don't have access to technology all the time. Assuming you have a reference sheet with this table on it, you can still work backwards and get only this accurate, no more, but this is accurate enough. All right. If you still have questions, you can hang out. Let's look at the, frankly, let's look at the better method. This is, it kind of runs through the full process. Okay, so I don't know that we need to consider this, but if you want to come back and look at the presentation on the Canvas page, you can kind of read through this. This is just, I gave a hypothetical scenario. And there we go. So we have two methods for checking for the p-value when using a t-value. Okay, I already said that, sorry. The second method is to use your calculator. And when we were working with a z-test, we can just use normal CDF. And we can calculate the area underneath the curve. Now we can do the same thing using a t-distribution. So we use normal CDF for a normal distribution, binomial CDF for a binomial distribution. So I think this should make sense. We're going to use t-CDF for a t-distribution. Okay, it's actually a lot easier, but it is good to know how to use the table. All right, I think I go through and explain this. So you want to go to your distributions menu, and you'll see option 6 is t-CDF. You just need to hit 6 and you'll get there. So you can put in the t-value that we got. That was negative 3.260. All right, this is kind of an important thing because this is where you might run into problems. If your t-value is positive, we're going to be finding the area above it. So you're going to have to use that test statistic as the lower bound. But if your t-value is negative, in our case, then you're going to find the area below it. So you're going to use your test statistic as your upper bound. All right, and again, just to put that on a diagram so it makes sense, if your test statistic is positive, it'll be over here, and you want that to be your lower bound with infinity as your upper bound. If it's negative, you want that to be your upper bound with negative infinity as your lower. then you just need to put in the degrees of freedom and calculate your p-value. So I'll do that real quick. 6, my my upper bound is the negative 3.260. I had 18 degrees of freedom. And I got 0.00217. Okay, and I want to remind you of the result we got when we went to the table. So when we looked at the table, we didn't know the exact value, but I knew it had to be between 0.0025 and 0.001. And when we calculate the exact p-value, we can see it does fall in that range. Okay, so is this making sense?
How'd you get that p-value?
This one right here?
Yeah, I got like something way different. Oh, my bad. I put in 18, not 28.
Okay. Oh, wait, no. You should have put 18 in. So my actual parameters are going from negative infinity. The upper is negative 3.26. 18 degrees of freedom.
Okay, I got it. Sorry, I answered it wrong still.
Okay, no worries. So very good. That is probably the easier way, since you will have calculators available. That's going to be the way you want to get your p-value. Okay. So now you can see the test statistic formula is here. This is not on the formula sheet. This is substituting in your statistic, parameter, and standard error. Okay, so here's the basic process. This is your one-page review of how to do this if you look at the presentation later. Write your hypotheses and determine your significance level, and determine if it's a one or a two-tailed test. All right, you want to check your conditions for inference, these three right here. And remember, when you're doing this, checking for normal, the sample size must be 30 or greater, or the population must be approximately normal. We're going to calculate our test statistic, and we're going to draw a diagram and find the p-value, the area under the curve, which is the p-value, assuming the null hypothesis is true. And then we want to interpret the p-value in relation to the significance level. Okay, I'm not going to dwell on this. This is kind of the same thing we did on Thursday. So let's look at, we have two practice problems to go through, but one of them really is more review of Friday rather than stuff we're doing today. Okay. I kind of want to, I want to change this problem a little bit because I already did this problem in fifth hour. I'm going to change this up a bit. Let's go with, I'm going to change that to 1,000 quarter pounders. So you, being the skeptical statistician that you are, you seriously doubt that the quarter pounder from McDonald's lives up to the name, which that refers to the pre-cooked weight of the meat. You investigate by getting a job there and sneaking in an accurate scale. Over the course of a week, you sample the uncooked weight of 1,000 quarter pounders. And I'm going to add this right here. You randomly sample the uncooked weight of 1,000 quarter pounders and find an average weight of 0.240 pounds with a standard deviation of 0.18 pounds. Is McDonald's a factory of lies? Okay, so let's start this off and figure out our hypotheses, our significance level. Is this one or two-tailed? So let's just start with the hypothesis. Or no, let's start with, is this going to be a one or two-tailed test? So let me ask this question. What would our alternative hypothesis be for us to determine if it's a one or two-tailed test? So if it's a two-tailed test, what would our alternative hypothesis have to be?
Is the weight not equal to a quarter of a pound?
There you go. So are we concerned with it not equaling a quarter pound, or are we concerned with it being greater or less than?
Not equal to.
Okay. Any other thoughts on this? Here, we'll answer that question in a second. And I'll start by saying, Zach, you're not wrong, but we could have difference of opinion. Okay. So the null hypothesis, what would our null hypothesis be for this problem?
It equals a quarter of a pound.
Okay, we're talking about mu here equals a quarter pound, 0.25. All right, the alternative is that mu, Zach said, is not equal to. Does anyone think it should be something else?
Would it be less than
All
0.25?
right. Now, I think the subtext in the question is that we think that it's less than a quarter pound of meat, because no one's challenging, like getting upset if they get more hamburger. Well, very few people would complain. But to Zach's point, if we are not sure, remember the more conservative thing to do is to say not equals. So the most conservative thing to do here is not equals. So that's not a wrong answer, but we're going to move forward like this. Okay.
So does that make it one-tailed?
There you go. Now it's a one-tailed test because we're only checking to see if it's less than the mean, less than the presumed mean.
Yeah.
Okay, and what significance level do we want to use here?
.05.
All right. This is where we kind of get to decide, but just as a reminder of kind of research ethics, it's really easy to run a test and then look at what your p-values are and then determine after the fact what your significance level is. So if you ran a lot of tests and you got, 0.06, 0.04, 0.09, 0.32, and 0.06, it's really tempting to say, I'm going to go with the 0.05 level. So therefore that one's significant. You can't kind of do that after the fact. It needs to be done at the beginning. And keep in mind that your significance level plays no role in the calculations that we do. It's just to compare at the very end. Okay, so we decided 0.05 will be our significance level at the beginning. Now, this is kind of the state part of our problem. Now we're going to plan this out. We know this is going to be a test. What is the name of our test? Anyone know? Excellent work. So one sample t-test, really that's good enough. You can just call it that. Or you could say, oops, not of, for mu. Okay, so make sure that you're able to communicate that in your answer. Now you don't have to call it that. If you just mention somehow that we had one sample and it was a t-test, then you're good. You don't have to name it exactly the way you see right here. And we will learn about 2 sample tests with the next unit. So then it gets a little more complicated calculations wise, but now it also gets more complicated because you have to determine, is this a 1 sample or a 2 sample test? And you have to determine that before you can move forward. All right, so anyways, now we're gonna check our conditions. Is it random, 10%, normal? All right. Is it random?
Yeah.
Yes, it is. You'll notice that it very clearly says random right here. And it wasn't just haphazardly inserted in there to meet the condition. All right, 10%, do we meet that?
Yes.
Yeah, I think it's fair, since we're using this, maybe not the best setup for a test, but this is less than 10% of all quarter pounders. And I know it's just one location, but you want to add a caveat to that at the end, you can. Is it normal?
Yeah.
It is. Well, I was just answering. I was going to ask, but whatever. N is greater than or equal to 30. We don't know if the population is approximately normal. I would guess that it is, but regardless, it doesn't matter because we had over 30 in our sample. So yes, it's normal. We can move forward. Okay. Now we want to actually do some calculations, and we will start with our generic test statistic, which is that the test statistic is equal to, I was about to say the wrong thing. It's going to equal the stat minus the parameter. Again, this comes straight from the formula sheet, divided by the standard error. Specifically for this, we are working with means. So that's going to be T equals X bar minus the mu divided by sample standard deviation divided by the square root of n. And now I can substitute in specific values. What is X bar?
.24.
0.24. Mu is
0.25.
0.25. It never says 0.25 in the problem, but this is where you just, okay, a quarter pound is 0.25, and we've got that right here as our null. Okay, our sample standard deviation, I'll just show that as 0.18. And the square root of n is 1,000, so I'll just do square root of 1,000. I'm going to go ahead and calculate the standard error separately, because that'll be good to know here in a second. So 0.18 divided by the square root of 1,000. There you go, 0.00569. Oh man, I think I went overboard with this. No, it'll be good. So I divide that. So 0.01 divided by that number gives me negative 1.757. And just as a reminder, this is our T test statistic. So I still want to keep going because all I've done so far is I've set up a sampling distribution that presumes that the average is 0.25. And of course, I've got 2 standard deviations away. And negative 1.75, about right here, is going to be my test statistic. I want to find the probability of getting that value, negative 1.757 or lower. So now I need to calculate this, which is the p-value. We've got the test statistic. We use this to find the p-value. And when we do this, we need to make sure that we are using TCDF. Okay, so I will put my answer up in just a minute. Okay, and hopefully you guys got the same thing. I'll give you guys just a little bit of time to catch up and go through that. Okay, so I want to conceptually run through all the work that we've done here. And anyways, we started off with the null hypothesis that these really are a quarter pound. And then we had an alternative hypothesis that says, you know what, maybe it's less than a quarter pound. And they're jipping us as far as a little bit of the meat goes. We set a significance level. So we checked conditions before we could do any calculations. And of course, that's what we did there. We want to make sure all those conditions are met. Now, the heart of this is the calculation of the test statistic. We needed to, first of all, plug numbers into this. And just remember that this is essentially a z-score calculation. And we're figuring out how many standard errors our result is away from the mean. And we got negative 1.757. We are 1 3/4 standard errors away from the presumed population mean. Okay, so knowing that, now we want to figure out what's the probability of getting that. The probability is this area right here that I already have an arrow drawn to. And we calculated that with TCDF. We got 0.0396. There's only a 4% probability of getting that result or more extreme. So now we can conclude this. Okay, and we have kind of a template for it. Hopefully I have enough room to write it all in. It says, because the p-value is less than the significance level, or the alpha level. And here I'll just summarize, I'll say 0.0396 is less than 0.05. We reject the null hypothesis. Okay, and there's a little more to it. We say, we have convincing evidence that the true mean weight of uncooked patties is less than 0.25 pounds. Okay, lots of excitement. So of course this is being recorded, so if you guys need to go through a sample like this again, you can kind of watch this. Your homework tonight is basically 4 scenarios set up, or you need to run through, and determine if you get a statistically significant result or not. So I will say this is a full, complete answer, and I would expect you guys to be able to run through all 4 parts of this. Okay, are there any questions on this before we move on to another practice problem? Okay, so we are looking at angiograms, or during an angiogram, that is. Heart problems can be examined via a small tube called a catheter threaded into the heart from a vein in the patient's leg. It's important that the company that manufactures the catheter maintain a diameter of 2 millimeters, and the standard deviation is very small. Each day, quality control personnel make several measurements to test the null hypothesis that the mean is 2 millimeters against the alternative hypothesis that it's not equal to 2. And there's significance level 0.05. If they discover a problem, they will stop the manufacturing process until it is corrected. So the first question is this a one-sided or two-sided test?
Two-sided
It's two-sided. How do we know it's two-sided?
because the alternative hypothesis is not equal to.
There you go. And that's the giveaway right there. Very good. So in the context of the problem, why would this be important? What do you think?
Because our p-value could be either negative or positive.
It could be, yeah. But more specifically, like, think about what that means. If the true mean is greater than or just not equal to 2, what kind of problems would you have?
That would basically be like any error would reject the null.
Yeah, and that's partially it. I think what we're trying to get at specifically is, this is an actual catheter going into someone's leg and then up to the heart, which it's weird to think about. But anyways, I think it's pretty important that it's exactly the advertised 2 millimeters. So though we don't know exactly the reasons why, I think a smaller than 2 millimeter tube and a bigger than 2 millimeter tube would both pose problems. So we want to make sure that, we are right at that. Don't want it to be too big or too little. And we want to check that it's just not equal to. And that makes it a more conservative test because we're more likely to reject the null at this point. But that's good. I'm jumping ahead. Let's actually see if that's good or not. So what happens, in this context, what is a type 1 error going to mean? Does anyone remember a type 1? Are we rejecting the null when we shouldn't, or are we failing to reject the null when we shouldn't?
We're rejecting the null when we shouldn't.
Okay, so type 1, we rejected the null and we shouldn't have. What are the consequences here? So let me, just to get some thoughts here. what happens if you reject that it's really 2 millimeters, what you're producing?
They don't put it in you.
Well, they don't fit, but like what is, well, remember the type 1 error says that it really is 2 millimeters, but you rejected it. So it really is a good product, but you rejected that it is. And what does this mean?
You're throwing
As far as
away a
it goes.
good catheter.
Yeah, you might have to throw away a good product. So and then what else does it say in the text of the problem? What else do they do if they discover a problem?
They stop manufacturing it.
Yeah, they stop production temporarily, but they do stop production, and time is money, right? All right, so those seem to be the main consequences here. Type 2, you fail to reject the null when you should. What's the consequence there?
You're putting too big or too small catheters inside people.
Yeah, using faulty products on patients. Okay, and therefore, which one seems to be worse?
Type 2, because you could like seriously injure someone.
Exactly, yeah. So I think we're seeing a lot of scenarios where the type 2 error is the worst one. And I think a lot of times when you're dealing with medical things, there's maybe better to be safe than sorry and to reject the null rather than accidentally accept it when you shouldn't have, or fail to reject the null. Anyways, now I mentioned at one point type 1 is maybe the worst error. And I think in academic papers that can be true. There's a lot of, remember, type 1 is whenever you reject the null and you shouldn't have. And there's a lot of people who do the p hacking to come up with a statistically significant result when really there's nothing there. It's just random chance. But they keep massaging the data and maybe doing some ethically questionable things so that they can get a statistically significant result. So academically speaking, type 1 is sometimes like, I don't want to, it's hard to put a value judgment like it's worse, but maybe in academic papers, type 1 is more prevalent. And so it's going to come back and look bad on you when you get that. So maybe in academic studies, it's better to fail to reject when actually the alternative was true. It's better to have a type 2 error. But again, everything is context specific. And hopefully these ideas, you do have to think through like 3 layers of abstraction here in order to understand the type 1 and type 2 errors. But it's really, really important you get that down. Okay, and that's all for today. Let me show you your homework. I'm not going through another practice problem, but read chapter 21. I did do things in a little bit of a different order. Maybe I should have flipped Friday and Monday, like I mentioned, but we're going to stick with this. I posted a worksheet. There is not an answer key, so you're going to have to answer this the best you can. But this is a great opportunity. If you look at a problem and you do not understand one or all of them, come to class tomorrow and we can look through those and get it all sorted out. Okay, I have spoken enough. You have yourself a wonderful day and I will see you tomorrow.